The first project we're going to talk about is the ARC. It's one of the latest projects that we finished. It is the newest project that was actually built at the Green School. We can see for the context an overview of an aerial shot of a part of the school area. And we're talking about the building that's down here. Right now we see the old gym and are talking a bit about how the new one is fitting better with the design and how we actually got to the space. As in context, the project is based in Bali, in IBUKU, which is close to Ubud. And it's located within the boundaries of the Green School, which was founded 2008. And we can see a few of the impressions of how bamboo can actually create a different alternative learning environment where it feels really close, connected to the nature, with classrooms that are actually getting the students connect really well with the surrounding and get a closer touch with it, and how open the structures actually can be and invite the students to really learn and basically lift up their minds. A part of the jungle is the ARC. We can see it here. It's the gymnasium for the school. And the project was finished in 2021. And it's now one of the tallest bamboo structures. And we think it's the tallest freestanding bamboo structure in the world. It's roughly 800 square meters of an area. And the interesting part about it is mostly the structural element. We see here an overview of how it's settling into the land and how we have different kinds of curves and valleys getting created in natural kind of waves that are representing leaf openings and really spanning the open space that we see inside, that is used mostly for basketball or the normal school sport. When we look at the floor plan, it's a pretty straightforward floor plan. We have a system of different arches that are covering the main area. And you can already notice that they are basically always crossing in one element and then leaning at each other to get the triangulation. And then they're connected in the center in between with the grid shell. And it's a real special part about this building and why it's such a huge success is because it's a really good example of how architects, engineers, and carpenters can collaborate together. It was a building that was done by PT Bamboo Pure as the constructor, IBUKU as the main architectural designer, Adriel one for the structural concept, and Jörg Stamm also part for the structure, but also the carpentry behind it. And what is really impressive to see is that it's a hybrid system in the structural way, where we have an arch system for the main structure that is taking the forces of the wind and the earthquake. And then we have as a composite to strengthen it in the vertical way with the grid system. So we have a grid system combined with the normal arc system that is building the triangulation in the system. It is a building that's roughly 40 meter high. It's spanning over a width of roughly 20 meters, which is due to the size of the sport field. And it really gave us a lot of challenges how we can actually get a height inside the building that's allowing students to freely move in the space, but also to allow us to get enough light and wind in. For example, in the elevation, we can see that we have different openings in between the different shells and roofs. That is really allowing us to get a natural ventilation inside. But also in the evening hours, there's this beautiful light reflection that is coming through the pine trees that's then getting reflected back into the building to really optimize the space.
Yeah, and also this reflected lights can make a special effects when we see it. When we see inside the building into the ceiling, it creates this some kind of soft reflection to the ceilings, as you can see here. I mean, this is also a good light effects that are created by the skylights and the air hole, and just make it more beautiful.
What is really interesting in the way that the building was actually made achievable is that here in Bali, we have really high skilled carpenters. And if you look at the buildings that IBUKU came up with in the last couple of 10 to 12 years, you will quickly realize that they're getting really complex because bamboo is never really growing as a straight pole. And none of the bamboo is identical, and everything is really thought in the three-dimensional space to really connect it with the nature. And because of the shape and the design language that got developed over the years at IBUKU, it's really hard to capture it in plans. For sure, you can make the normal elevations, sections, and floor plans, and you would be able to get an idea as a high-skilled architect of how the space would look like. But it's really hard to get those informations transferred the right way to the carpenters. And that's why here in Bali, our most important tool is actually to build a physical bamboo model, which we are doing to scale. And you can see the construction model here in the background. It's giving us an input of how we want to have the first rough ideas of connections, how the grid shall be laid out, but also how we can have different control points within the space. And what's happening when we go to the construction site is that the carpenters, they have the set of drawings, but they also have always the construction model next to them. And they have a ruler that they take and they measure the bamboo pole in the model. Then they go to a big pile of bamboo that's provided on the site. They find the pole that's fitting the best, bring it in space, and then actually lock it into the building. And it's something that's probably done only here in Indonesia, maybe in Thailand. Yeah. And it's very valuable, not just for the carpenters, but also for us as designers to get a feeling of the space early on, to really be connected with the material, because in the 3D, it would be easy to draw the most perfect curve and the best arc. And then once you actually start building it in the model with the bamboo stick, you will quickly realize it will just snap apart because the radius is not achievable. And with that, we always getting pulled down to our feet from the three-dimensional world. We have this strong connection to the beautiful material that we designed with.
Guys, can you explain a bit about the design process? This pattern or something that was traditionally in the country, or you have to design this geometry specifically for this goal?
Yeah. So the design process was very engineering driven. We worked early on a concept from Jörg Stamm, who is a master carpenter and an expert when it's coming to bamboo construction, in cooperation with Adriel, the structural engineer from the UK. And we quickly tried to find ways how we can get strong bamboo arches that actually allow us to span over a distance of 20 meters, which was never done before in bamboo. And during all of this time, our job as an architect was to find a beautiful composition that's playing with the surrounding area that we have. In the background, you can see parts of the canopies, but it was mostly the urban context to the heart of school, which is at the right end of the field, to really think how we can put it in a place that it's fitting right into the landscape, but also the existing design language. And what the engineers came up with was, in the beginning, not the idea of having a composite structural system, but the idea was quickly born that we want to have an arc system, because it would be easy to pre-build the arcs on the ground, to lift them into position. And it's a technique that's a bit more traditional to our area, but normally it's supposed to be beam structure and not the typical arcs. And what we've done a bit before, you will also see it later, was building a small yoga dome in Ubud, where we used the first time parametric design. And this really allowed us to prefabricate the arches, to find the right connection points. And this is basically taking it to the next level with a different structural concept. And once the engineers were able to tell us that we can do the arc structure, we quickly realized that because of the earthquakes, the movement in the x-axis, like in this direction, is actually not optimal because everything is in the same direction. So we needed to figure out a way how to get the cross civilization with the triangulation. And that was just done by flipping the two arches over to get the first crossing. And then the connection on the top to build like the next taller triangle. And it worked really good in the x-axis, but in the y-axis, we then didn't have this triangulation. And that's where the engineers came up with the idea to put a synclastic element of the grid shell in place, because it's really good in taking the forces in the y-axis. But the problem is, since it's a different kind of structural system, during an earthquake, the bamboo would move differently. So they had to figure out a way to have kind of a buffer zone where the bamboo can actually get a bit more pushed together or extend again, because bamboo is really strong in compression and in tension, but the shear forces are really weak. And that's where they came up with the idea of the grid shell. And even if you come to the site now and during the construction site time, walked a few times to the top, and you realize that it's still a tiny bit flexible as a roof structure. And that's basically the idea behind it. And then once we figured out that we need to have a grid shell system together with the arches, the next big question was, what kind of material can we use for the roofing? And we tried to figure out ways of using a more sustainable membrane, which was supposed to be a hemp structure, a hemp textile with a bioepoxy, but it would have driven the building costs way too high. And it would also have stiffened up the building too much. And then we ended up using something, if I go back, what we call plu-plu. It's flattened bamboo shingle. And it's a traditional roofing system that is used in Bali and Indonesia for many years. But it also helps us by layering it in different directions to get more triangulation in the shell system.
And bamboo structure is such a new concept personally for me. Is bamboo naturally able to handle this much of pressure by itself, or you have to do some sort of chemical engineering or make any difference in the structure to make this happen? Like, for example, in some wooden structure, I know they use heat to make this arc shape and make it possible to make this complex form.
Okay. I don't think the chemical engineering is doing much thing to the structural power. The bamboo itself is strong enough if it's engineered correctly. Since we are designers and architect, we don't have that. We have the knowledge, but we need to make sure that our knowledge is right. So that's why we team up with some of the greatest engineers to make sure that our design is strong and the bamboo is being carved and shaped nicely to endure the forces from earthquakes. And I think that's it. And to make the curve, there are several ways that have been done in Indonesia, but the most common one is, we call it rup. That is the easiest way to curve bamboo for Indonesian carpenters, because it's we've been doing it all the time.
Maybe to come back to the chemical aspect of it. I mean, the beautiful part about bamboo is it's a natural building material, and it's biologically designed in a way that's really efficient. If we think about modern structures and steel buildings, if we want to produce a steel pipe, we always get it in a tube shape because it's the most structural, stable, geometrical shape. And bamboo is already growing naturally in that. And the difference between bamboo, which is the grass type, and actually wood, is that bamboo is built out of different vascular bundles and different kind of fibers, exactly, that are running all the way from the bottom in one line to the top. So if you would go and take a bamboo and you peel off a tiny bit of the skin, you can actually pull it all the way to the top of the bamboo. And bamboo is the strongest on the outside. And the more you get inside the flesh, if you cut it in the horizontal and then look on the top, the more weaker it's getting. And it's really optimized by nature to make it efficient in the structural way, in the weight to strength ratio, basically. Because of that, bamboo is behaving really good in tensional and compression stress. You can compare it to the weight ratio, which is similar to steel. But when we look at the shear forces, so if we would start twisting it, bamboo is getting really weak again. And you can only get around this in a structural way. But when it's coming to using chemicals, we only use a salt solution to protect it against bugs that would come and eat the bamboo from the inside. Besides of that, the bamboo structure is really kind of honest way of building types, because we have a natural kind of design philosophy that we are following. Bamboo is weak when it's getting wet and when it's exposed to sunshine. And for that, there's always the comparison to Paddington the bear. So if you want to design with bamboo, you want to have long overhangs, which is the rain hat that he's wearing. Then you want to raise it from the ground, which is mostly the raincoat. And then he's always wearing his rubber boots. So we always make sure that the foundation, the first point where the bamboo is touching the foundation, is at least 30 centimeters above the ground. And this way we make sure that it's not getting in contact with water or direct sunshine, because then it would get weaker. So it's mostly natural and design techniques that are protecting the bamboo, making it really efficient and allow it to live for a really long time.
Do you know how many years such a structure lasts without any need of repair or any like a special condition?
I mean, it's a really good question. So if you design well with bamboo and it's treated the right way against the insects, right now we always calculate that it can last 30 years because we don't have any reference data. Most of our buildings are about 15 years old and they don't have any sign that they get weaker, which is really nice to see. But there's not enough data or example projects yet to really prove how long a bamboo building can stand. Back in the days, there were traditional buildings that could last until 100 years. I think the oldest bamboo building was supposed to be over 200 years old, but no one really did the science behind how long it can really last, because we haven't been in this field for that long time.
Amazing.
And I guess we're really curious about bamboo because we don't. Although here in the Philippines, there are some architects who use bamboo, but myself, I'm not that well familiar. So what's the if you can treat a bamboo? You said it could last like 30 years, and the oldest would go for 200. But what if it's going to be left untreated? Like, what's the shortest lifespan of a bamboo, I think?
Well, it depends on the environment of the site itself. If it is not treated in the solid solution that Lucas mentioned before, probably it will get eaten by the bugs. Especially in Indonesia, there are so many bugs that loves to eat wood and bamboo. So that is the first thing that we have to do with the bamboo. As long as the insects notice there's an untreated bamboo structure, then we will not guarantee it will be lasting, like it will be short. So the first thing I would recommend is to treat the bamboo from the insects with the solid solution.
Yeah. Sometimes in Indonesia, you see people that use bamboo as a fence. And after 2 years, it's starting to be getting eaten up. After 3 years, they have to redo it. So if you don't treat the bamboo well, it's actually getting eaten off quite quickly. And that's also the sad part about bamboo, because it created a stigma in the society here in Asia that bamboo is a material for poor people, because only poor people were building out of bamboo because they didn't have the money to build a proper house. But since they didn't know how to treat it, it really got weak very quickly and had to be redone again and again. And that's one of the things we try to fight currently with our designs, because if you can show people what's possible with bamboo in such an amazing and breathtaking way, which is kind of magical in a few buildings, it's really making people to rethink their idea and first impression that they had with bamboo, and actually moving forward and realizing, okay, bamboo is actually better than I thought. And then people are getting more interested again as well.
Yeah, and then I'm just curious, since I can see from the drawings here that, and from the images that you have like you it's not like only one bamboo strand, like, right? So you make a compression of several bamboos. So what if like one bamboo gets rotten or destroyed? Is it easily replaceable as a structure?
Yes. So in this structure, what is really nice to see, as you mentioned before, there are really heavy loads because we had a really long span to bridge over. So we use a technique when the radius is getting too tight to bend it in a naturally way, where we cut in 2/3 of the bamboo in between a node. So the bamboo is having the nodes and the internodes in between. And if you cut in the center of it 2/3, you're able to tighten the radius a bit more. It's called wap-wap, that Fred already mentioned. And it's a traditional technique that's efficient to create tight radius, but it also weakening the strength of the bamboo, because the fibers are running always in this direction and all the way from the bottom to the tip. And then you can imagine if you cut it in for 2/3 of the structural integrity is actually getting lost. And one of the ways to balance it out is to bundle the bamboo. So here you can see bundles of 6 bamboos that are always getting connected in between. Here we see one of the metal dowels that we use. It's getting connected in all the different locations, every 70 centimeters. And it's already helping to strengthen it. But when you look at the length of the arch, the longest were about 26 meters long. You can imagine none of the natural bamboos are actually growing this tall. There are a few species that you can use that are actually growing up to 30 meters, but bamboo is tapering extremely. And because of that, you only use a length of about 8 meters from the center, because in there you can guarantee that the tapering is less than 1 centimeter from the bottom to the top. And those sections you can connect again. And then the bundling is basically a guarantee that the forces in the parts where you have the cut or where you have the connection is actually supported by the pole above it. So if you imagine that this bamboo pole would not have been treated the right way and it's getting bad, you still have 5 other members that are surrounding it that is able to take the load for that. And normally when we start designing the buildings, we always have a safety calculation inside. So you would not be relying on 6 of them, maybe 4 already enough. But just in case that there's a crack somewhere or one bamboo pole is not treated the right way, we know that the other members are taking over. If the bamboo is getting really damaged, you can take out just the section and put a new part inside to repair it. Or in other buildings, we had it that you can just replace it. So depending on the complexity of the structure, you can replace it. But I think in the green school, there were only 2 bamboo poles that had to be replaced over a time of more than 10 or I think it's nearly 15 years now. And it's because during the first constructions, they didn't knew how to treat it the right way now. But with time moving on, we're getting to learn more and more about bamboo. There are new techniques, new treatment systems. So now we use the borax boron type and different kinds of soakings. So it's getting more and more safe to use them.
Yeah, that's good to know. I'm actually really learning a lot about bamboo right now.
Yeah, same.
So maybe a last question for me regarding this project. If we could go back to the form of the roof, is there other like a concept behind it aside from you mentioned it's for like thermal comfort and ventilation? Are there like other, perhaps like an inspiration or you wanted to achieve the form that you want to convey to people, apart from just the technical engineering side and the more the thermal side?
So, what we think if we design a gym on this case, the most important thing is the space and the proximity of the balls. For example, if they are playing basketball, the height of the roof have to be high enough for the ball to move freely without the players worrying about the height of the building. And so we decide the form to be high enough for every sport that are common in Indonesia. And then the form and the structure follows the function, follows that height consideration that we are deciding. And for the shape itself, I think this building is following the consequences of the function priority that we are concerning. In this case, is the height of the building.
And what's also nice to mention, of course, a lot is really defined by the engineering and the structural needs, but you can see it's having really nice rhythm where you have longer parts and it's getting closer in the top and stretching out again. And the same with the entrance rays. So we always have a rhythm that's kind of following the movement of the people that are using the space. And you can see it a bit better after the construction was done in the detailing. You can see that even in the grid, it's not a perfect grid where we have perfect squares. We always wanted to play with a natural kind of language and a different rhythm because different types of sports are having like elements where you move faster, where you move a bit slower, where you want to have elements where you can rest. And that's basically in the details where the real design work is actually coming to life. And the shape is also symbolizing that. It's used a bit more to play with the landscape of Bali because we have 3 main volcanoes in the hillside and the landscape. So that's where the different shapes and openings are coming from. And then, of course, optimizing the daylight use and the natural circulation.
Yeah, there's actually a lot to consider when you're designing with bamboo. Now that you've explained it, and I think you really have to be like have an like a artistical leaning towards when designing this, right? Because you can't just
Yeah, that's
design
for
it
sure.
Yeah, for sure. You have to have that like a creative intent on it.
I mean, it's a very sculptural approach in this sense, because you always think about the building. Sometimes we think about the building not as a house. Sometimes it's a being. Sometimes it's an addition to the nature. Sometimes it's just an extension to your mind that's actually enhancing the space and really bringing it out forward into the nature. So it's basically blurring the borderlines of what we have, what we feel, what our emotions are, and how we can connect to nature in the wider sense.
So nice. Yeah.
Amazing. And guys,
okay.
I have my final question from this project. Can you explain a bit about the foundation of this structure? Because I can imagine it's not just gonna handle the load in the gravitational axis. It's gonna keep it from the collapsing, something like that, because it has this type of bow-shaped structure. How you make this foundation possible? How did you make it stuck in the place?
Yes, so with the foundation, I mean, in this project it was interesting because it was a rebuild of a gym that was standing before there. So we already had the floor installed in place. We based it on the foundations that were there before. So we already had a concrete pile foundation below, and we just planned to put the touchdown points on the same positions. And the way it's working inside, we have a concrete foundation. Sadly, we want to use a more sustainable material than concrete to create the foundation, but at the moment, the market is not really open for it. There's not a lot of alternative. But this concrete column is actually going down a couple of meters below the ground. And then it's having reinforcement steel inside. So we have the different rebars that are coming out of the pedestal, the concrete pedestal. And then it's basically bent over in the direction of where the bamboo is going. And what we're doing after that is we poke holes through the different knots of the bamboo to really lift the arch onto the position and place the reinforcement bars inside. And then we cut off like small holes, like you can see here, about 70 centimeter to a meter above the bottom of the bamboo. The most important part is that you at least have one knot that you're going through it, because the bamboo has different chambers. And then we fill it with concrete. So we basically reinforce it and bind it to the reinforcement bar that's in the center to really bring the forces down over the pedestal into the foundations and then onto the rocky ground.
Wow, guys, I have to admit that even though the bamboo structure looks simple, but you have to consider a lot of factors to make this happen.
Yeah, it's more complex than I actually thought.
Most of the structures.
I mean, this structure is probably also the most complex bamboo structure existing in the world, because you have different types of structural concepts that are combined. We have a really long span. It's free spanning. It's having a high height. So it's a really complex and advanced project in the bamboo world. In the beginning of the days of IBUKU, there were a lot of post and beam structures that were in theory a bit more simple. One of the best examples is Shama Springs. If you want, we can also jump to it and show a few pictures from there.
Yeah.
Yeah, sure.
It was before. And it's probably the most advanced post and beam structure, but in a way that it's still simple. You have the beams that are going to the top, and there you see how the posts are connected to the beams and basically framing it in the position. And that's a technique how IBUKU started. And still with this kind of relatively simple social system, we already achieved to create very beautiful natural shapes that are more similar to leaves. So it's kind of a biophilic design approach and biomimical, but in a different kind of natural material context. And I would say it's still its own design language that got involved maybe 10 years ago. And it's still evolving every day that you come to the office, that we work with Laura and the rest of the team. And you can see it's 24-meter high. It's probably the highest bamboo building in Bali because the limits are already to the maximum. But it's showing what is possible with kind of simple techniques if you really pay the attention to the detail and trying to figure out new concepts, how you can implement it.